Thank you all for coming. It has been a tradition in our department to award the Bock Prize once a year. And this year in particular, we are fortunate to have not only Bart Bock's grandson, Alex Bock, but his daughter as well, who's named Priscilla Mackenzie Bock. And she's named after the wife of Bart Bock. As I mentioned, both of them were astronomers. And she will become very soon, within a few weeks, the second Dr. Priscilla Bock in the family. She's defending her PhD in a couple of weeks on history, which is somewhat related to astronomy, because astronomy can be regarded as history of the universe. Let me say a few words about the Bock Prize. This is a gift of an anonymous donor to establish a prize in honor of Professor Bart Bock. And in his name, the income to be used for a prize to be awarded preferably biannually on the recommendation of the astronomy department to a recent holder of a PhD degree in the physical sciences from Harvard or Radcliffe who is under 35 years of age. The award to be preferably based upon a doctoral thesis, book, or research paper in the area of Milky Way research by observational methods. A few words about Bart Bock. He was born in 1906, was a Dutch-born American astronomer, teacher and lecturer. He's best known for his work on the structure and evolution of the Milky Way galaxy and for the discovery of the so-called Bock globules, which are small, densely dark clouds of interstellar gas and dust that can be seen silhouetted against the brighter backgrounds. Bock suggested that these globules may be in the process of contracting before forming into stars. In 1928, he attended the IAU assembly in Leiden, the Netherlands, and met Priscilla Fairfield, back then. She was an associate professor in astronomy, and then he fell in love with her and proposed to her, and they married. He moved to the U.S., where they both got married in 1929. And then the Bocks remained at Harvard University for almost 30 years, from 1929 until 1957, where he taught astronomy and directed the Harvard Observatory. Later on, he moved to other positions. For example, in 1957, the Bocks moved to Australia, where Bart took up the position of director of Mount Stromlo Observatory in the Australian National University, ANU, in Canberra, where he was to hold this position for the next 9 years. And he was a pioneer in the use of the electronic computers for astronomical observations, and the first person to use them for any purpose at the ANU. So he has many important contributions in his record. And we are awarding this prize once a year to our best former graduate student. And this year we decided to award it to Meredith Hughes, who is an assistant professor of astronomy at Wesleyan University. She finished her BS in physics and astronomy at Yale, and then arrived to a better university for her PhD. She graduated in 2010 and was a Miller Fellow after that at UC Berkeley for 2 years, and then became an assistant professor of astronomy since 2013 at Wesleyan. She received many awards, one of which is the Fireman Fellowship for outstanding PhD thesis here in the astronomy department, and many of us remember her work, exceptional work here. And while she was doing her PhD, she also spent one afternoon every week at the Museum of Science, interacting with the public. And I had a chat with her about that. She found that very important, but also somewhat exhausting, different from teaching in the classroom, because of the repetitive nature of conveying the same message a number of times. But Meredith is an excellent teacher, and she has already 2 students working with her, and she did exceptional work mentoring them, and as she will describe, she's also doing exceptional research. And I would like to invite Alex and Priscilla to give her the award. But before we do that, we have a special gift for the 2 of you. A very small gift. And please go ahead. Meredith.
Congratulations. Thank you.
Thank you so much. And one other thing, Peg Hurley was able to locate one of the remaining copies of Bart Bok's biography. And we are pleased to give it to you.
Oh, thank you.
And we hope to be able to get used copies for future years, but this may be the last one that we give.
Wow. Thank you.
And so today we will hear from Meredith on circumstellar disks and planet formation with ALMA. That has been the focus of her PhD, and she did many important works on debris disks and also gaseous disks around the young stars.
Thank you. Thank you all so much for having me here, and in particular, thank you to the department and to the Bok family for the incredible honor of being awarded the Bok Prize this year. I can't even tell you what a pleasure it is to come back for this purpose. So today, I guess that means I get to tell you about some of the research that I've been doing since I left here 5.5 years ago. And so today I'll tell you a little bit about the work that I and my group at Wesleyan University have been doing for the last few years on studying circumstellar disks and planet formation. In particular, now we're in the era of ALMA, which is a very exciting time and place to be research-wise. So I always like to start off my talks with 2 images. One image that shows the technique that I use to do my research, which is millimeter wavelength interferometry. So, of course, this is the process of allowing radio light to enter the apertures of all of these different radio telescopes and combining it to synthesize a much larger telescope. So with all of these little telescopes, we put the light together so that it's as though we have a giant telescope that stretches basically from the farthest apart dishes in the array. We have the power of seeing details that are very small, even though the individual telescopes that we use in this array are also pretty small and on their own don't give us a lot of angular resolution. So ALMA has been a totally transformational instrument in this field. The other image that I like to show is an image of the science that we do here. So this is a young star, and you can see here's a disk of gas and dust around it, and there are a few planets forming in the disk that seems to now be in the process of being cleared out. And this is not an ALMA image, right? This is an artist's impression. But the joke that I like to make is that now that we have ALMA, I don't have to show artists' impressions anymore. I can just show you the real thing. And so that's really been the incredible thing with ALMA coming online now, is it's giving us these unprecedented, detailed views of the process of planet formation around nearby stars. So I wanted to start off with an overview of the process of star and planet formation to make sure that everybody's oriented to exactly which stages I'm going to be talking about today. So stars form in giant molecular clouds of gas and dust. The densest parts of those clouds collapse under the influence of gravity, And then you wind up with this fairly messy stage where you have a protostar, possibly surrounded by some kind of a pseudo-disk. Maybe there's an envelope that's falling onto the disk. Maybe there are outflows coming out. And then eventually all of this settles down into something that looks more or less like this, a pre-main sequence star surrounded by what we would call a protoplanetary disk of gas and dust. And this is really, between these stages is where all of the action happens with planet formation, because these are the gas-rich stages where there's lots of gas and the dust is sort of responding to the gas dynamics and clumping together. And, if you want to make planets like Jupiter and Saturn, you've got to make them before all of this gas disappears. Eventually, all of that primordial gas and dust dissipates somehow, and we wind up with something that starts to look more like our solar system, a main sequence star, possibly surrounded by a debris disk, possibly including planets. So today I'm going to be talking about these last two stages. And before I move on and get into some more of the details, I wanted to show you, so this is the very cartoonish version of the process of star and planet formation, right? But I wanted to show you some of my favorite actual images of these two stages that I'm going to be talking about today. So my favorite images of pre-main sequence stars, other than the ALMA image of protoplanetary disks, other than the ALMA image that I already showed you, come from the Orion Nebula, which seems appropriate because I'm going to be talking about a particular disk in Orion today. So here's the constellation Orion, and if you look right in the sword right around here with the Hubble Space Telescope at very high angular resolution, you see these beautiful images of these, the points of light in here are the young stars. The colorful background is the light of the background nebula that gives that part of the Orion constellation that reddish glow there. And the smudge of dark stuff that you see around these young stars is actually the shadow of the disk. So the background nebula is bright, and it can't shine through these dense dust disks. So we see the shadow projected 1,000 light years towards us, and that's what we're looking at in these images, are the dense disks of gas and dust. The cool thing about looking at these with radio telescopes is that it goes from being just a shadow to the dust actually glowing, and you can see through the disk material and measure how much stuff there is and how it's distributed. My favorite image of a debris disk comes from a little bit closer to home. Here's one of my favorite images of a debris disk. So for those of you who don't know, the Earth has not, or the solar system has not one, but two debris disks, we think. This one is called the zodiacal light. And so if you go to a dark place right at sunset and you look at the western horizon right after the sun sets, sometimes you can see this finger of light coming up above the horizon. And that finger of light is sunlight that's scattering off of little dust particles that are generated by primarily by collisions between Jupiter family comets in the inner solar system. So that's our inner solar system debris disk. It's the one that looks brightest from Earth, but if we were alien astronomers observing our solar system from another star, it actually wouldn't be the brightest debris disk. The brightest debris disk that we would see would come from dust in the Kuiper Belt when our Kuiper Belt objects interact and smack into each other once in a while. And that dust disk, because it's larger and there's more stuff going on out there, would actually look brighter to us from a different star system. So many of the debris disks that I'm going to show you today are basically scaled up versions of our Kuiper Belt, the belt that Pluto is part of in the outer solar system. So just a little bit more about circumstellar disk evolution before I jump into some of the details of what my group is working on. I've been talking about these two end stages. The protoplanetary stage, these disks are found around pre-main sequence stars. Some of you who are at the ITC lunch have seen a slide that looks very like this earlier today. But these are found around pre-main sequence stars. They're very, very gas rich. 99% of their mass is in gas. And the dust is more or less primordial. Maybe the dust grains have started to stick together to grow bits of planets, but it's all dust that's left over from the formation of the star. By contrast, debris disks are found around main sequence stars, so older stars that are a little more mature. They have no gas in some cases, as far as we can tell, or relatively little gas. I'll talk to you a lot more about gas and debris disks later on. If I'd been giving this talk, 10 years ago or something like that, I would have just said, debris disks don't have gas and moved on. But now we're finding that actually some debris disks do have a substantial amount of gas. So at the end of my talk, I'll tell you a little bit about that interesting field of study at the moment. And the dust, when we look at the properties of the dust, we find that it must be constantly replenished, presumably by grinding collisions of these Kuiper Belt-like planetesimals around other stars. And then if you're, like I said, if you're interested in planets, you've got to be interested in this transition from protoplanetary to debris disk, because this is what sets the deadline for giant planet formation, especially the formation of Jupiter and Saturn analogs in our solar system. They have to form before all of the gas dissipates. So some of the questions that I'm going to talk about today are, how does environment, particularly in this protoplanetary disk stage, affect planet forming potential? Does it matter if you're located in a low mass or high mass star forming region? What are the dynamical conditions during planet formation? And that's sort of code for how much turbulence is in the gas in these gas-rich protoplanetary disks. That's something that my group is very actively working on. And finally, what is the origin of the very little gas that we are now finding is more and more common in these debris disks? So a bird's eye view of my talk involves first looking at protoplanetary disks, and I'll have two sections that are on protoplanetary disk. One is on the effects of environment. The second is on the observable signatures of the viscous transport process. Again, that translates to turbulence in gas in protoplanetary disks. And then at the end of my talk, I'll talk about disk dissipation, and in particular moving into this debris disk stage. And I'll talk about these observations of molecular gas and debris disks and what they're telling us about the planet formation process. Okay, so first, planet formation in high mass environments. This, remember, we're talking about the protoplanetary disk stage. And in this part of the talk, I'm highlighting thesis work by my student, Sam Factor. And just to give you a little bit of background about where this project came from, Sam was a physics and computer science major at Wesleyan who, his senior year, decided for fun to take an astronomy class. He took astronomy with me, and he got so excited about it that he was like, hey, can I stay and do a master's thesis with you? And I was like, yeah, okay, why not? So Sam signed up for our master's program, and in the year and a half after he finished the introductory astronomy class, really caught up and did all of the work required to get a master's degree. So when I was thinking about a project for him, I was like, okay, I better make it something kind of small and self-contained, something that he can do relatively easily, because, you know, he's never done astronomy before. And as you'll see, he not only did more than I expected in this project, he also made a really neat serendipitous discovery as part of this project. So this is Sam's work, and Sam is now a PhD student at the University of Texas, Austin. He just started a few weeks ago. So we all know that stars form in many different environments. This is a gorgeous wide field IRAS image that I really like that shows a lot of the nearby star forming environments that we tend to study because they're the relatively nearby and bright ones. So just to give you an idea of how these environments are different, I wanted to point out that Taurus Auriga, the Taurus Auriga star forming region, which is 140 parsecs away, is up here. And this is the area where, before ALMA came along, this is where we were studying most of our protoplanetary disks. And the reason for that is because it's one of the closest, it's in the northern hemisphere, so it's easy to observe. And, you know, we didn't really have a choice about low mass versus high mass star forming regions because the alternative, the closest high mass star forming region that has a lot of these disks, is down here. This is Orion, and it's about 500 parsecs away. So we didn't really have the sensitivity and resolution with the submillimeter array to do a lot of the work that we would like to do on disks in Taurus Auriga in this high mass star forming region in Orion. But just looking at this image, you can see that the conditions in Taurus Auriga versus Orion might in fact be very different. We call this a low mass star forming region because it's dominated by low mass stars like the sun and even less massive stars. And then it's not until you get to Orion that you start to enter a region where we're forming high mass stars, which are very energetic, and some of the O and B stars that form in the Orion star forming region are sending out these massive amounts of ionizing radiation that are literally evaporating the protoplanetary disks before our eyes. And there are also Hubble Space Telescope images of this. So when ALMA came online, there were a few observations with a submillimeter array of sort of basic dust properties of disks in Orion. And one of the first things that we wanted to do with ALMA is to follow it up and try to get comparable resolution and sensitivity to what we had previously gotten in Taurus Auriga, now in a massive star forming region like Orion. So that was a project that was led by Rita Mann. She was primarily interested in the dust in these disks. So here are 3 Hubble Space Telescope images of protoplanetary disks in Orion. And you can see what I was mentioning earlier in my talk, that while these are just shadows of the dust disk that we can see with the Hubble Space Telescope, in radio light they start to glow, and we can really see the dust glowing in these disks and measure the amount of mass and the surface density structures in these systems. Rita came up with a lot of really cool results, a few of which I'll tell you about in a minute. But along with this data set, there was some observations of gas in some of these systems, which we had never been able to observe in a high mass star forming region before. And so one of these systems that was very gas rich, I decided would be a great master's thesis project for my student Sam. So environment does matter, and we know this from looking at the dust in these protoplanetary disks, which we can't study in a lot of detail. We don't have a ton of spatial resolution yet, but we can draw some general conclusions so far. So here's a plot of the inferred mass of the disk. So the way that this works is we measure how much mass is in dust, and then we multiply by 100 because we just sort of assume that there's a 100-to-1 gas to dust mass ratio because that's what the interstellar medium looks like. So these are approximate total masses of stuff in these disks. 10 Jupiter masses, roughly, is a special mass because this is the mass of something called the minimum mass solar nebula, which is sort of a theoretical construct. That's what you take if you take all of the planets in our solar system, grind them up into bitty pieces, add enough gas to bring the composition up to solar composition, and spread them out throughout our solar system. If you do that and you figure out, okay, how much gas did I have to add, how much total mass is in this theoretical minimum mass solar nebula, that's the minimum amount of stuff we had to have in the solar system to form the solar system as we know it today, it was about 10 Jupiter masses of stuff. So this is like our solar system, and these are the masses of protoplanetary disks as a function of their distance from this particularly bright ionizing source in Orion. So you can see that if you're close to this source in Orion, and I should say this is projected distance, it's hard to tell when we're looking with a telescope whether two objects that look this far apart on the sky are actually this far apart on the sky, or whether they're actually this far apart on the sky, because we only get the two-dimensional view, not the three-dimensional view. So this is projected distance, but we still see this important trend, which is that if you're close to this massive ionizing source, you cannot form a disk that's as massive as the disk that we think formed our solar system. But once you get about 1/10 of a parsec away, you start to have a significant fraction of these systems that are massive enough to form a planetary system like our own. So that was a neat result. So environment matters because of our distance from massive stars. The other reason environment matters is that when you have high stellar density, the chances that two stars will come whizzing by each other and disrupt the other's disk is higher. So we want to look for evidence of that as well. So the question is, how do these factors affect planet forming potential? One way that we wanted to look at this was by taking this disk right here. This is seen in scattered light again and with the Hubble Space Telescope data. And based on the Hubble Space Telescope images, the idea was that it was a solar analog, so a star kind of like the sun, in the environment where we think the sun formed, which we think the sun formed in a high mass star forming environment like Orion, rather than a low mass star forming environment like the Taurus-Argov region. So here are the gas observations. This is one of the lines, HCO+. The most abundant species in these disks is molecular hydrogen, but it's invisible to us. So a lot of times when we're studying these disks, we study carbon monoxide. But in Orion, the problem is that there's so much carbon monoxide in the cloud and it's hot that it actually obscures most of the carbon monoxide emission from the disk. Not all of it. We can see the line wings that are at very high velocities, but most of the emission we can't see. But if you go to some of these higher critical density tracers like HCO+, you can actually see a fairly uncontaminated circumstellar disk. This is a roughly Keplerian disk around this young star. And in fact, these lines are showing you Keplerian rotation profiles for a 1, 2, and 3 solar mass star at this distance and with the correct orientation, geometrical orientation. So we got this nice molecular line data, and Sam was working on imaging it. Or modeling it. So he did some modeling of the temperature and density structure. I won't go into the details here. Here the colors are the density, and the lines, the contours with the numbers are the temperature in the disk. So he puts together this two-dimensional model of the disk structure, then sort of turns it into 3 dimensions. He includes photodissociation and freeze out. So in the midplane, it's so cold that all of the HCl plus and carbon monoxide is in solid form. Those happen at slightly different temperatures for different molecules. And then photodissociation is when energetic radiation penetrates the top of the disk and starts pulling apart molecules. So you don't have molecules above this line, and you don't have molecules in gaseous form below this line. So we get this sort of skin on the disk. And then he takes a radiative transfer code and says, okay, given the orientation that this thing has, what should this look like on the sky? He turns that into fake interferometric data, which we then compare with the interferometric data from ALMA, and we're able to draw some conclusions about the disk. So the main results from Sam's study are that when we put together surface density profiles from these two molecules, HCO plus and CO, and we compare them to a typical surface density profile from the Ophiuchus star-forming region, which is this black dashed line here, or if we compare them to the minimum mass solar nebula, and this is the minimum mass solar nebula inferred for Saturn, Uranus, and Neptune in our own solar system, we see that they're basically on track. So despite this disk being in one of these massive star-forming regions, it still seems to have fairly uninterrupted planet-forming potential. Now, it's true that this one is relatively far away from the massive ionizing source. However, it could have been disrupted by stellar flybys or some of these other environmental effects. So this is actually something that's fairly useful to know. And it really is the gas that's allowing us to study the surface density profile in detail, because the gas disk goes out really far. So we do have to kind of extrapolate back in, but we actually get several resolution elements around the disk, which we can't do with the dust, which is more compact. So this is kind of a neat surface density profile plot. Another thing that was interesting is we can get a dynamical mass of the central star. So just by looking at the Keplerian rotation pattern, we can say, how massive is this star? Remember I told you it was a solar analog? Well, it turns out it's not a solar analog. It's actually about twice the mass of the sun when we get the dynamical mass. So that tells us something interesting actually about the spectrum and the scattering off the dust, which Sam discusses in his paper. But by the way, I should mention these error bars do not include systematic uncertainties such as the distance. The systematic uncertainties would be about 15 to 20% in this case, but it's still pretty clear that it's a 2 solar mass star rather than a 1 solar mass star, give or take. And then the really cool serendipitous discovery that Sam made is that when I showed you this plot before, here's one side of the disk, here's the other side of the disk, and if you look, there's the disk sort of stops up here. And if you looked for the symmetric stopping place down here, it would be right here. We didn't notice this at first, actually. There's a lump down here. And we didn't notice it. We started modeling it like a disk, and all of our fits were really bad. And so we were like, what is going on? And we had, I don't know, it's one of these research things, right, where you go down a rabbit hole, and Sam was like, maybe I should model it as an eccentric disk. So he wrote this whole eccentric disk modeling code, which was really awesome and we'll probably use for something else. But clearly that was wrong. And when we looked at it in more detail, we finally figured out that actually, no, what is this? If we look at this clump, this is the x-axis here is the offset from the center of the disk. And you can see it's not quite at a 0 offset. It's a little bit to one side. We actually see this in a couple of channels, and so we can measure, and it's fairly high signal to noise, so we can measure with some significance exactly where it is. And the offset, the spatial offset that we measure along the major axis, we've seen lumps and line wings like this before, high velocity features before, but always when you image them, it's not a lump right on the disk major axis. It's like a big blobby thing, like an outflow or something. This, when you image it, it's right on the disk major axis at exactly the separation and velocity that you would expect if it were part of the Keplerian profile of the disk. So this is something that seems to be in Keplerian rotation in the disk. It's right next to the star. With some of the other molecular lines, we can see that this disk actually seems to have a hole in the molecular gas in the inner disk, and this is right inside the hole. And if you estimate the mass from the HCO plus data, it comes out to a mass of about 6 Jupiter masses, and its location and speed are Keplerian with a distance of about 40 astronomical units from the central star, whereas the disk extends out to hundreds of astronomical units. So we basically come up with 2 possible explanations for what this thing could be. One is it might be sort of a gas vortex that's part of, we see these vortices that sort of trap dust particles and help them grow into planets in protoplanetary disks. And these have been seen with ALMA before in continuum emission, but we've never seen a gas signature before. But the other possible explanation, and we're working on ways to distinguish between these explanations now, is that it could be the envelope of a forming protoplanet that's cleared out a gap inside the disk. So this was something that we were not expecting to find in the data at all, and it actually turned out that this semester, and this past spring semester when Sam was working on this, there were several theory papers that came out saying, hey, here's what the signature of a forming protoplanet in a disk might look like, and it looks remarkably like this thing that we were looking at in our ALMA data, including one of Ilse's papers. I don't know if Ilse's here, but she wrote a really nice theory paper on that. Yeah, there she is. So we're working on coming up with follow-up ideas for how we can distinguish the vortex idea from the protoplanet idea. But this was a really exciting feature that we just found serendipitously in this data set. So that's basically Sam's thesis right there. The next thing that I wanted to talk about is turbulence in protoplanetary disks. And my main collaborators on this project are Kevin Flaherty, who's a postdoc working with me at Wesleyan University, and Jake Simon, who's a Sagan Fellow working at Southwest Research Institute in Colorado. And Jake's our theorist. He keeps us honest. So I'll tell you a little bit about turbulence in protoplanetary disks and what we're learning. Again, this is the protoplanetary disk phase that we're talking about. So first of all, why should you care about turbulence in protoplanetary disks? The reason is that turbulence is very important in the process of planet formation, and we don't really understand how. We know that turbulence can, in theory, both solve and create problems in planet formation, and I'll walk you through a few of those now to just sort of motivate what I'm about to tell you. So we think that turbulence is the main source of viscosity in these disks, and viscosity is what causes the disk surface density structure to evolve. So another way of saying that is that when we talk about viscosity in these disks, for a viscous accretion disk, you can predict how the evolution is going to proceed with time. And early on, it starts off more massive, the disk starts off more massive and smaller. And over time, it spreads and thins until the surface densities are lower and the disk is larger. And so the amount of viscosity determines how quickly this happens and the way in which it happens. And so you could say that viscosity is responsible for determining when, where, and how much material is available for planet formation, if this is the process that's actually determining the evolution of the disk. So that's important. Another way that turbulence is important theoretically in planet formation is that it can prevent solids from settling to the disk midplane. When these disks form out of giant molecular clouds, they start off with the gas and dust all mixed together. And if you want to form planetary embryos, in the most common theory of how planets form around these young stars, you have to bring the dust grains together first, and then they accrete a gas envelope. So to have that happen, we think we need these gas disks to allow the solids to kind of settle out, to sort of gravitationally settle towards the midplane. The gas is supported by pressure, but the solids are not, so they should be able to gravitationally settle. However, if the disk is very turbulent, it can prevent that process of settling, prevent the large surface densities from accumulating in the midplane, and prevent, or at least inhibit, the process of formation of planetesimals. So the amount of turbulence can affect how quickly this settling process happens. But turbulence can also promote planet formation by promoting the coalescence of solids in the disk because of this phenomenon that is one of the ways in which we understand a possible solution to the meter size barrier. So this is a real problem that happens in planet formation, which is we have a pretty good idea of how little things stick together in disks, like submicron to micron to up to almost centimeter size things stick together in disks. And we have a pretty good idea of how big things stick together in disks. Once you have Pluto-sized things or larger, they stick together by gravity, and that's pretty easy. But that jump over a size of about a meter is actually really hard to explain theoretically, because those size particles should be smacking into each other pretty often, pretty fast, and pretty destructively. So one of the ideas for how we can jump over this meter size barrier is when we have turbulence in the disk, it creates pressure peaks and minima, and the solids want to come towards the pressure peaks. So if you can collect enough solids in one of the pressure peaks, enough tiny little solids in one of the pressure peaks, they can sort of jump over the meter size barrier, gravity can hold them together, and then suddenly you've got a big thing. So there's a role that turbulence might play in creating solids by creating these pressure peaks in which the solids can collect. And then finally, once you've formed a planet, turbulence is important because it can change both the rate and direction of planet migration. So normally planets migrate, they start off in a disk, it's nice and laminar and smooth, and they sort of migrate smoothly in towards the star. But if the disk is turbulent, it can affect that rate and direction. So they might sort of stochastically migrate in a little, and then out a little, and then in a little. And so it affects how quickly this happens, and also the direction to some extent. In general, they're going to have to keep going in, but they can have little reversals that can have effects on the final configuration of planetary systems. And then I put a little et cetera down here because this is just a sampling of ways in which turbulence affects the planet formation process. There are more. I just wanted to give you an idea. The point of this slide is turbulence is really important in planet formation in a lot of different ways. And so what we want to do is to place observational constraints on how much turbulence there is and how it's distributed through the disk. So how can we measure turbulence? There have been a number of attempts at this over the years. I probably won't go through these in a lot of detail, but one way is just looking at accretion rate measurements. So if you measure how much, so I mentioned to you that we think turbulence is the source of the viscosity that drives the mass evolution of the disk. If you're going to thin and spread material in the disk, you'd better also be sending some material in to conserve angular momentum, and we think this is why these disks are accretion disks. So if you measure how much stuff is falling onto the central star, the accretion rate, in other words, then you can get a sort of global estimate. You can try to back out how much turbulence did you need to drive that rate of accretion onto the central star. So that's good, but it relies on a lot of sort of theoretical assumptions about what's going on in the outer disk, and you can't tell from how much stuff is falling onto the central star how the viscosity and the turbulence might change with position through the disk. So you want to get something that's a little more spatially specific. One way of doing that is by looking at row vibrational lines. These are, this is a CO bandhead line in the infrared. And if you fit the particular wiggly shape of this row vibrational line, you can learn a lot about the disk. And in particular, these authors have found, Carr and Nijita and some of the other authors on this paper, have found that you really need to broaden the lines more than you would expect just from thermal broadening and rotational broadening. And in fact, you need turbulence that is roughly transonic, so roughly at the sound speed, to fit the CO bandhead emission in some of these disks. Now this is cool. This is some of the first evidence, direct evidence for turbulence in the disk. The limitation here is that these CO bandhead emission lines come from only the optically thick surface of the disk and only at a particular radius where where these transitions are excited. So you kind of get 1 point in understanding how turbulence is distributed through the disk. So ultimately, you'd like to have a method that could give you more of a spatially resolved idea. And that's where millimeter observations come in. And from sort of the early days of imaging the gas emission from protoplanetary disks, people have been fitting models to low-resolution carbon monoxide spectra and including turbulence as a parameter. The problem was that with some of these early observations, as you can see, the spatial resolution and signal to noise aren't very good, but also the spectral resolution of these observations was large or comparable to the amount of turbulence that we expected in the disk. And it's always dangerous to look for an effect that's smaller than your resolution, right? So what we really want is we want high spectral resolution, we want high sensitivity, signal to noise, we need it all to make these very sensitive, detailed measurements of turbulence in the disk. So as part of my PhD thesis here, we tried this with the submillimeter array once the submillimeter array introduced a new high spectral resolution mode. So we took some really beautiful observations in this high spectral resolution mode with the submillimeter array and made some of the first measurements of turbulence in the disk. For TW Hydra, we got an upper limit, a pretty low upper limit actually. For the time, that was very impressive. And then with HD 163296, which is this disk here, we had a tentative detection, roughly 3 sigma detection of about 300 meters per second. Then Stefan Guillotot and collaborators made a really beautiful measurement, not with carbon monoxide like we'd been doing, but with the CS molecule, which is heavier, and therefore it has a lower thermal line width, so turbulence is more pronounced relative to the thermal line width. So that was a really cool analysis. They got a measurement of about 100 meters per second in this other disk, and then we got ALMA. And we started to be able to really look at these disks in detail. And so ECR de Gregorio Monsalvo et al. Made a measurement of the same disk that I had observed a few years ago, but now with ALMA data, and got a lower turbulent line width. So the challenge here with all of these observations is it's really hard to distinguish turbulence from all of these other sources of broadening in the disk. So one thing that we've been thinking about as this field has sort of been growing is how can we do this in a statistically robust way, distinguishing these different sources of broadening. And that's why I say here also, we really need good statistics. The thing that's missing from all of these measurements, including my own, is good error bars. There aren't any error bars up here, and that's for a reason. Most of these were just made with a chi-squared minimization where, you check chi-squared, is it lower here than here? Okay, good, we're done, right? But what we really want to characterize is what is the uncertainty on these measurements of turbulence given all of the degeneracies in the modeling process. So that's what we've been working on at Wesleyan along with my postdoc, Kevin, and then we've also been working at it with theorists coming from the other direction and saying, okay, what level of signatures should we see and what should turbulence look like in these disks given the MHD simulations? So this is from the paper that Kevin has submitted. We got the referee report back. It's great. So he's just responding to the referee report now. So this will be coming out very soon. This what we're doing is we're taking a nice modeling engine that assumes LTE, and we've convinced ourselves that assuming LTE with these carbon monoxide observations is not so bad. And this is actually based on a code that Catherine Rosenfeld wrote as part of her beautiful observation of the HD 163296 disk. This is publicly available ALMA data that Catherine analyzed and demonstrated in really exquisite detail that from these observations, basically from the fact that we get this sort of double loop structure, here's a loop and here's a loop, we're actually resolving the vertical temperature structure of these disks, which was one of the main degeneracies in the fitting process with turbulence. And this is something we can do with ALMA data that we just could not do with previous data. And so that's making our measurements much more precise of the turbulence in these systems. And so then we're combining it with an MCMC code to do a statistically robust sampling to really try to understand our error bars on these turbulence measurements and including the degeneracies with other parameters. So we're working on good statistics. I'm going to hold off on giving you the answer for now while I tell you a little bit about the theoretical effort that we're also working on. So we're trying to meet in the middle with the theorists. And this is from a paper that Jake and I worked on together over the last year as well, where these are some numerical simulations of turbulence in these disks. The key variables here are the ratio of gas pressure to magnetic pressure and the penetration depth of far UV photons into the disk, how far in surface density they penetrate into the disk. I don't know, this is all theorist stuff. So we ran a bunch of different conditions and we looked at sort of what is the range of turbulence that we get out and what are the signatures of turbulence when we then take the results of Jake's numerical simulations, graph them onto a realistic temperature and density structure, and predict ALMA observations with them. What do we see? So this is basically the answer to what do we see. This is a bunch of simulated spectra from Jake's observations with these different conditions. And the way to think about this plot is this is a simulation with no turbulence, and then we have increasing levels of turbulence in these different simulation conditions. And does it look any different? Can we tell the difference? This looks pretty different at first glance, right? Until I tell you that this error bar here is a characteristic error bar for the systematic uncertainty on the flux scale of ALMA data. So with ALMA data, the sort of channel-to-channel uncertainty, the noise in different channels when we take a spectrum like this, is controllable because you can always increase your observation time or look at a brighter disk, or you can control it in various ways. The systematic uncertainty is the scaling factor that you can scale these things up or down on the whole. You can just scale the whole thing up and down. And that's basically out of our control. That has to do with how well we understand flux models of solar system objects and other things. So there are ways to try to beat this down, but you can't beat it down a whole lot. So this was discouraging when we found this. We were like, I don't know, those don't look very different when you worry about the systematic uncertainty. So instead of looking at the spectral profiles on their own, we normalized them and looked at the shapes of the spectral profiles. So we basically took out the systematic uncertainty. And you can see that actually the line profiles do have different shapes. And you can imagine that if you get enough signal to noise, you can distinguish between these different shapes. And so one thing that we looked at was we made up this metric called the peak to trough ratio to look at how different the line peak was from the line center. And we sort of made a plot of, okay, what is the peak to trough ratio, that's the colors in this plot, as a function of the amount of turbulence in the disk and taking into account the plus or minus 20% uncertainty on the temperature that we get from the systematic uncertainty on the ALMA data. Because basically the absolute flux levels tell us temperature in the disk. These are optically thick lines. So that's the main thing that they're telling us. And so what you can see is that, yeah, there's some degeneracy. There's a little bit of slope here. But to a large extent, the gradient in peak to trough ratio comes not from the temperature. This is all kind of blue across here, mostly blue. This is kind of reddish, orangish, greenish. This is all red and orange up here. But you get the rainbows when you start to look at turbulence. So the peak to trough ratio is a more sensitive tracer of turbulence than it is of the systematic uncertainty, at least on the scale that we expect with ALMA, with the range of turbulences that we expect based on the MHD simulations. So that was something useful that we learned from this modeling exercise. And the other thing we can do is we can use these different ways of looking at the data that we've come up with by thinking about the theoretical data when we analyze the ALMA data. And this is what we came up with. So this is a paper from, this is a figure from Kevin's paper, and this is a figure from Jake's paper. And over here, the black line is the data. The red line is the best fit model with basically no turbulence, so less than a couple % of the sound speed turbulence. And the blue line is with the level of turbulence that was predicted by the theoretical simulations and that we detected the tentative detection that we had had before and that Itziar de Gregorio Monsalvo had derived from the ALMA data. So you can see that the higher level of turbulence does indeed predict this more subtle peak to trough ratio, whereas with our data, we're seeing a much deeper peak to trough ratio that's consistent with essentially no turbulence in the disk, and that's borne out in our statistical analysis. And the other thing I want to remind you all is that we are not just looking at spectra here. This is three-dimensional data, and so in the paper with Jake and in Kevin's modeling, we're actually considering all 3 dimensions. And it turns out one other thing that we learned is that spatial resolution is really crucial for providing strong constraints on turbulence, especially if you want to use an optically thin line that gets you down to the midplane or closer to the midplane. So you can see here, this is a model with no turbulence. This is a high temperature model, and this is a high turbulence model. And you can see the differences where if you look at the line peak, for example, the temperature brightens the emission for sure, but the turbulence broadens the emission and makes this hole in the middle smaller. This hole is big, this hole is small. So the differences are subtle in the image domain, but now finally with ALMA, we have the angular resolution and the sensitivity and the spectral resolution all at the same time to make these sensitive measurements of turbulence, and we're able to place extremely good limits on the amount of turbulence in the disk that are much lower than were expected theoretically. So that's where we are with our turbulence observations. I think it's an exciting time, and I think it's nice that theory and observations are coming together in this way with our understanding of turbulence in these disks. So finally, at the end here, I want to take a few minutes to talk about molecular gas in debris disks. So now I'm talking about this transition to the debris disk stage, and more particularly about these debris disks that we have mostly assumed to be gas poor historically. This is thesis work, undergraduate thesis work, by my student Jesse Lehman-Sifry, who he worked with me for 2 years as an undergraduate, and he was one of the most spectacularly productive undergraduates I've ever had work with me before. I'll tell you a little bit about his thesis project today, but then he stayed over the summer after his senior year and wrote a whole other paper on a whole other topic. He's really just an amazing scientist. Too bad for us, after he graduated, he decided no grad school for now. He was going to Colorado to do a lot of mountain biking and work in the tech industry. So I think that's probably a good decision for him, but maybe he'll come back to astronomy research someday. So the standard story that we tell, which I told you at the beginning, is that protoplanetary disks have lots of gas and dust left over from the formation of the star. At an age of roughly 10 million years, the gas and dust disappear, and we're left with just this debris dust that's generated by grinding collisions of planetesimals. So if that's the case, then what's this? This is a spectral energy distribution that shows the star, and then some dust emission at long wavelengths. And if you're a connoisseur, you might realize that the relative amount of dust emission compared to the photospheric emission, the infrared excess, is low, and that tells us that it's an optically thin disk, which indicates a debris disk. So we would see a SED like this and think, okay, this is a debris disk. Except then you take a molecular gas spectrum and you find out that it actually has a significant amount of molecular gas remaining, which is a surprise. We've known about this for a while in the sense that Ben Zuckerman wrote a paper in 1995 looking at the gas content of a bunch of these disks. And in fact, 2 disks that we would probably classify as debris disks on the basis of their infrared excess did indeed have detections of a substantial amount of molecular gas in them. So, and then there are other observations. For example, this is a Hubble Space Telescope spectrum of the Beta Pictoris disk, where you can see these signatures of carbon monoxide in absorption. Beta Pictoris happens to be observed edge-on, so you've got like a star here and then an edge-on disk over here. So the star provides like a beacon that shines through the disk, and this absorption spectrum tells you about all of the cool molecules and things that are in the disk. So this is a gas observation by absorption that Aki Roberge did. But one of the cool things about ALMA and millimeter wavelength interferometers in general is that we now have the sensitivity and resolution to make spatially resolved observations of the gas in these disks. So we knew it was there, but we didn't really know very much about it because we couldn't image it and see it around these young stars. So again, this is some work that I started while I was still a graduate student. This is one of my thesis observations here of 49 Ceti. A few years later, I went back with ALMA. This is data from last year. And with ALMA, this is the dust. This is what the dust disk of 49 Ceti looks like. It was too faint for us to image with the submillimeter array. I have this great graphic that I show sometimes that Jesse worked on while he was an undergraduate working with me, where he spent months reducing 20 hours of data from the Karma Observatory, and he got like a 4 sigma blob detection of 49 Ceti. And then this is 45 minutes of ALMA data, and it was like, all of a sudden we could see, right? All of a sudden we can see what's going on in these debris disks. It's really amazing. So this is what the gas looks like. When you do an analysis, you find that it probably has an inner hole and it extends out to several hundred AU. Similarly, the dust also appears to have an inner decrease in emission, and it also extends out even farther than the gas, it turns out. We now have a few more of these now that ALMA's come online. This is the only one that was imaged pre-ALMA. Now with ALMA, there is HD2 and 997. This is the dust. This is the gas. This one has a dust ring, and the gas seems to be totally continuous. And then the coolest one in a lot of ways is Beta Pictoris, where here's the dust over here. It seems to have a slight asymmetry. One side's a little bit brighter than the other. And then you look in gas, and the asymmetry just knocks you over. It's extremely asymmetric. So this is interesting because this is the only one of these disks in which we see a statistically significant asymmetry. So that might be telling us that this one is special in some way, or the question is it special in some way? With 3 disks, you can't really tell. So something that ALMA's been working on and that I've been working on in collaboration with John Carpenter at Caltech is, well, I guess he's at NRAO now, at ALMA now, is looking for more of these things. So we've discovered 3 new ones. So we've about doubled the sample of these gas-rich debris disks. Those are their spectra. Those are the gas images. These are the dust images. And now here's HD 141569 with ALMA as well. So this is the survey that I was working on with John Carpenter. In addition to what do these things look like, we also want to know how common are they? How often do we see this gas in these debris disks? So this is a survey of young debris disks, so debris disks with ages around 10 million years, give or take 10 million years roughly. And we had a sample of 24 of these, which we took spectra of with ALMA. And you can see these are ordered in spectral type from B to A through to the F stars down here. This one's sort of an outlier. This is AK SCO. It's not really a debris disk. A lot of people would call it a protoplanetary disk. It's kind of a funky object, but we have it on here anyway. So whether or not you believe AK SCO, it turns out that about half of the A star debris disks exhibit significant amounts of gas. There's actually a statistically significant detection in, I think, this one also. I don't know if you can tell from the spectrum, I couldn't. But when you image it, you can see there's actually like a 4 sigma blob in a couple of the channels. And then the F stars, Unless you want to count AK SCO, the F stars have no detections. So this is exactly the opposite of what you would expect if you thought about it ahead of time, because A stars have a lot of extremely energetic radiation that they're giving off all of the time that should be photodissociating the carbon monoxide really quickly. And so you would expect them to not have any gas left. Remember, these were all selected to be at ages of 10 million years, whereas the lower mass stars, the F stars, have less ionizing radiation. And so you might expect that their gas disks could persist a little bit longer. So what's going on? I don't really know. An aside, with all of these great gas observations, ALMA has also been working on dust observations and debris disks, and I wanted to just highlight 3 systems where the dust surface density structures have been studied. This is also something where previous interferometers couldn't do this because they didn't have enough sensitivity to take advantage of the resolution and actually get multiple resolution elements around the disk. Now with ALMA, we can learn about these surface density profiles. And there have been 3 that have been characterized in detail in the literature so far. AU-MIC by Meredith McGregor, who's here, which has a flux that increases with radius, the opposite of protoplanetary disks. HD 107146, which is generally increasing with radius, although it does have this decrement of flux in between. So it either is a double power law that looks like this, or there's a gap in the disk somewhere. But in general, increasing with radius. And then 49 SETI, which was part of Jesse's thesis project, which we know about this from near-infrared observations. There is an inner dust disk of small grains, but when we model the ALMA data, it's a broad, flat disk that's decreasing its surface density with radius. In a way, it's actually sort of the inverse of this system, because the overall trend is decreasing, but there's a little bump at this radius where there seems to be a narrow belt of excess dust emission. And if you had to bet, if I told you that only one of these disks had gas in it, which one would you bet? Well, one of these things is not like the others, right? So the one with the decreasing surface density profile has gas in it, and the 2 with the increasing surface density profile have extremely low upper limits on the gas density. With 3 objects, I don't know if that's a trend. Nobody's tried to explain it theoretically yet, but it's at least suggestive that something about the gas really changes the dust surface density profile in these systems. So just to go over, I don't have answers yet on this to answer this question, so don't get excited. But the question that we're all working on in this field that I think is one of the most interesting questions that ALMA is trying to answer with debris disks right now, partly because it couldn't be asked at all pre-ALMA, and now we actually have the tools to get at it, is in these gas-rich debris disks, we want to know, is the gas primordial? Are these Peter Pan disks that are refusing to grow up and dissipate their gas? Or is it second generation? Did they dissipate their primordial disks, and now we have this sea of evaporating comets or collisions between Mars-sized bodies that are somehow releasing large amounts of gas into the disk? And how can we try to answer this question? Well, we're starting to try to answer this question by looking at these 4 categories. The gas and dust morphology, are they in the same place? Do they seem to be undergoing the same physical processes? The gas mass and the lifetime. So the idea here is that if you can measure the gas mass and you can figure out how quickly it's being destroyed by the ionizing radiation that's coming from these stars, you can take a ratio of those 2 numbers and calculate how long it should be able to stick around for. The chemistry, if we look at the molecules that are present in the gas, is it more similar to a disk or a comet? And the frequency, are we seeing something common or unusual? So obviously, the survey with John Carpenter is a way of answering that. So let's see how the evidence stacks up so far, putting together all of the various observations that I told you about so far. Morphology, are they in the same place? So we can look at the 3 that have been resolved and analyzed in detail, and for 2 of the 3, the answer is essentially yes, and for 1, the answer is no. So just to boil it down for you, the evidence on this one is mixed. I won't go through all of the details here. Okay, so morphology is not helping us out a lot. How about the lifetime? When we calculate the gas mass and compare that to a photodissociation rate from the energetic radiation from the star, it turns out that the lifetime that you calculate for all of these systems is much shorter than the age of the star, and in fact is on the order of kiloyear, thousands of years. So all of the gas should be destroyed in about 1,000 years in these systems, and yet somehow they're persisting at ages of 10 million years up to about 40 million years, we think, for 49 SETI. So that would seem to point to a second generation origin. Chemistry, is it more similar to a disk or a comet? Well, so far with ALMA, we've only seen CO, although I have a very nice limit on HCN from 49 Ceti with ALMA. But from the optical lines, we know that 49 Ceti and Beta Pictoris are probably very volatile rich, which makes them look slightly more like a comet. So that's a little bit more of the second generation, evidence for the second generation origin. And then the interesting one that's left is the frequency. Are these disks common or unusual? So for a while I was saying, hey, free molecular gas with every ALMA observed A-star debris disk, because we started off looking at these big bright disks and they all seem to have gas in them. Now we know from John Carpenter's survey that that about half of the A-stars seem to have gas in their debris disks, and really hardly any of the F-stars have gas in their debris disks. Like I said, that's the opposite of what you might expect, but you can come up with various plausible alternative scenarios like, well, maybe it's the A-stars because they have a more massive underlying disk and there are more kind of comets to evaporate. That's a possibility. Or maybe they just had so much gas mass to start with that it's able to persist at these long stages, and we really just are seeing the last gasps for half of these systems. We don't see any CO around the F-type stars. The other thing about the timescale argument, though, is in general you can see the weight of the evidence is stacking up for second generation, but there's one problem with the timescale argument, which is that if you think this is a steady state second generation gas scenario, like you're constantly evaporating these comets to maintain the amount of stuff that's in there, you can calculate how many comets you have to evaporate per unit time. And it comes out to, for one of these systems, it's a Hale-Bopp every 5 minutes. So Hale-Bopp is a big comet, and we have to evaporate one of them. It's bigger than this. It's big. We have to evaporate one of them every 5 minutes. And if you look at the predictions for the reservoir of cometary material in debris disks, that's coming uncomfortably close to too much stuff, right? That's just a lot of stuff that you have to evaporate very quickly. So I would say that the frequency and the timescale arguments also have mixed evidence. There's the fact that we're seeing it primarily around A-stars argues, it's probably second generation, because how could an A-star hold on to its gas for this long? But at the same time, we have to worry about this timescale argument that if we are evaporating comets, it had better be, we'd better have a really big reservoir of comets in order to see these things around half of A-star debris disks. So we don't have an answer yet, but this is a really interesting area that a lot of people are working on in this field right now, and that I'm very excited to be working on as well. So just to summarize everything I told you today, disks around solar-type stars in Orion seem to maintain their planet-forming potential despite the environmental effects, and we've found something that may be a protoplanet envelope in formation orbiting inside the hole in the middle of this gas disk. So that's very exciting. With the high-quality ALMA data that we now have access to and good statistical analysis, we are starting to demonstrate that turbulence in at least one of these disks is extremely small, less than a few % of the sound speed in the upper layers of the outer disk, with signatures that are exactly the same way that theory predicts. So we seem to be converging relative to the theoretical simulations, although the level of turbulence is much lower than we expected. And the gas in debris disks is most likely second generation, but the primordial scenario has not been fully ruled out. So and also the surface density of these debris disks is becoming more interesting with ALMA. And I think you should all stay tuned, because there's going to be a lot more cool debris disk science that's coming out. These disks are still difficult to observe, so they're coming in one at a time, but there's really been an explosion of them in cycle 2 and cycle 3. So please keep an eye out for some of the exciting debris disk observations that are coming up. Thank you. I'm happy to take any questions.
I just wanted, before we take questions, to mention that although we are celebrating Meredith's beautiful research after her PhD, we should also acknowledge her PhD advisor, David Wilner, who is sitting somewhere.
He's right there.
Right there. A few questions. Go ahead, John.
I'm really excited about the possibility that it could be a factor of comets. You mentioned the problem that you have to evaporate tons of comets. And I'm wondering if there's other sources for that molecular gas.
Yes.
Could it be newly formed planets that are still maybe contain a large circumplanetary disk that are still contracting, and you're just not really resolving them, and you're just seeing all the gas in aggregate?
So I think the answer to that is no, because we can resolve these disks well enough that we can see that it's actually fairly uniform surface density gas around the disk, with the exception of beta pictoris. So I should mention that there are two, I was talking about comets, that was sort of shorthand for second generation, but there are two scenarios that I didn't talk about that have been proposed to explain this. One of those is collisions between two Mars-sized bodies. And so that might release quite a lot of gas if that kind of a collision happened. And that, I think, is a plausible explanation for beta pictoris, which is asymmetric. So beta pictoris is interesting because of that asymmetry. Any of these other situations are fairly axisymmetric, the prediction is, but a collision between two Mars-sized bodies could introduce that kind of asymmetry. The problem is that if you're going to see gas-rich debris disks around half of all A stars at 10 million years, collisions between Mars-sized bodies should be rare at that time. So or at least not that common, that if you look, you just happen to catch half of them in the act of a giant collision between two Mars-sized bodies. So there's a timescale argument that's different, that makes the two Mars-sized body collision difficult. The other explanation that I think is more plausible is you could have a planet in the debris disk, and that planet can induce resonance in the dust grains. And so if you have like the two resonant points, a lot of dust grains are going to kind of come through those resonant points at different inclinations and collide with each other and evaporate the icy mantles of the dust grains. So that's another kind of plausible scenario, in particular for the beta pictoris disk also, that seems to have a clumpier structure. The question is, is there then a process that can smooth out that gas axisymmetrically to give us something more like 49 Ceti and HD2 and 997, which do seem to be very axisymmetric in the gas.
And we do know that A stars form planets really readily.
Yep.
And beta pic actually has a moon.
Has a planet, yeah. Yeah. So that's certainly not out of the question.
Probably phase mixing may smooth it down. Two more questions. Go ahead.
So you mentioned this asymmetry that you see in the beta pictoris disk, and I was wondering how it relates to, I think that disk is warped, and
it is,
John mentioned it
yeah.
on the planet, so is that asymmetry on the same side? Like, how do those things relate?
Yeah, so beta pictoris is a complicated system. If I could change one thing about beta pictoris, it would be to tip it a little bit from exactly edge on, which is how we see it now, to even just a little bit face on, and we could figure out a lot more about it. So the problem with beta pictoris being edge on is that even though you have velocity information from the gas, it's completely degenerate. So if you see gas at a particular velocity, you don't know if it's in front of if it's in the front half of the disk or the back half of the disk, and it could be half and half, or it could be 0 and 100, or it could be any combination, right? So it's actually very difficult to get a sense of what would the face-on distribution of this material be in beta pictoris. And the warp we kind of see on both sides. It's like there's the disk plane with the star in the middle, and then in the middle the disk is warped a little bit, and we sort of see it going to both sides. So the asymmetry is on one of those sides. I think it is on the side with the planet, right? I'm looking at my disky colleagues over here. Yeah, Meredith's nodding. Okay. So yeah, I think the asymmetry is on the side that has the planet, although it's much farther out in radius. The planet is at a semi-major axis of, I think, about 10 AU, roughly, and the clump is out at many tens of AU, so like, I think it's 70 or 80 AU from the central star, so it's out significantly farther. So I think it's incredibly likely that there's some planet-related explanation for the asymmetry in the beta pictoris debris disk, but I want to keep in people's minds that beta pictoris is the weird one among these debris disks, and that none of the others seem to be asymmetric at any level that we can measure.
Last question?
I'm just curious, how stable is the luminosity of these A stars at this age? And the reason I ask is that if you have jumps in luminosity and you have billions of Kuiper belt objects at a certain distance, accompanying that jump in luminosity, you could increase the sublimation rate of ice, and that would be axisymmetric.
That's true. That's a good point. I haven't seen that one in the literature. My guess is that the issue with that, certainly the amount of ionizing radiation and dissociating radiation that these things get can affect the sublimation rates. But remember that most of these debris disks that we're talking about, the radii that we're talking about, are 100 AU away from the central star. So even though it will increase, it's probably not, stellar radiation is probably not the primary thing that's causing the dust grains to evaporate. That's why they have to they have to introduce the presence of this planet to sublimate the mantles of the grains through collisions, because that can turn the gas from the solid state back into the gaseous state. Otherwise, it would primarily be in a solid state. So you would need a huge influx of energy, and I think out at 100 AU, you're probably just too far away for the natural variations of the A star to do that enough that we would see as much gas as we do.
Well, there are many more questions, and feel free to ask Meredith after the end here. But let's all thank Meredith for a wonderful.